Okay, so he will talk about the projection strategy for choosing the regularization parameter of iterated Tikhonov method in Banach spaces.
Okay, thank you. Thank you to the organizers for inviting me and giving me the opportunity to show a little of my work. This is a joint work with Mahela Pentone and Antonio Leitao. Well, we are working Tikhonov regularization and in Banach spaces, and we are interested in the parameter of the regularization parameter, how to choose this parameter. So first, the problem we are interested in, this is this inverse problem, where A is a linear and bounded operator acting between Banach spaces. Our goal is finding this X here, the solution of the inverse problem. And we assume to have only an approximation for the right-hand side here, only Y delta. So we have these things in red, and we want to find X. We are interested, of course, in regularization methods. A regularization method is a method having this property here. For each pair Y delta and delta satisfying an equality like this, your algorithm, your method needs to give you a vector which in some sense approximates the solution of the problem. X plus is the solution we assume to exist in this case. And most importantly, this solution your algorithm returns with the noise level delta needs to approximate X plus as delta goes to 0. This is the regularization property. Okay, a very famous regularization method is the iterated Tikhonov method, which is defined using this functional here. We penalize here, in some sense, the distance between the previous iteration and the next iteration. And with a positive regularization parameter alpha. And then if we have a minimizer of this functional, we define the next iteration as this minimizer. Of course, some questions arise like how do you choose this parameter? This is very important for the performance of your method. Some popular choices for this parameter here, a priori choices actually, are these two different choices. The first one is choosing alpha constant. This is called stationary iterated Tikhonov. And if alpha is not constant, this is a common choice. This is a geometrical sequence. This is called the non-stationary iterated Tikhonov method. Well, a priori choices are good because they are easy to calculate and to implement, but they have drawbacks, like this one could be very, very slow. And this one you need to define this parameter, this number R. If this number is very close to 0, for example, then you have almost no regularization, and then your problem becomes unstable, your algorithm becomes unstable. If R is close to 1, you have almost in this situation, and then it becomes slow. It's difficult to say how is the best choice for this number. And you have control of this sequence, but you have no control, for example, how fast your method will converge or these kind of things. Okay, here a short outline of the presentation. First, I will present you a motivation in Hilbert spaces, how we define our strategy for choosing this parameter alpha. And then I will show you the method itself in Banach spaces. In the third part, I will present the results. In the 1 and 2, here I'm not very concerned with all the formality and all assumptions. It's only the main idea. In the third part, I will show the assumptions we need and what we can prove with them. Okay? So first, the motivation in our real Hilbert space. Okay, let's assume that we have no noise in this part, only for simplicity. We are with this point x0, we start with it, and we want to construct a sequence which converges to a solution of the inverse problem. I will show you how to perform one iteration from x0 to find x1, and then we repeat the process. Okay? So the idea is, in some way, we find a set omega which is closed and convex. And this set has this nice property here. It separates x0 from x plus in the sense that x plus belongs to this set and x0 does not belong to this set. I will tell you later how to generate this set. But if you have this set and you are in a Hilbert space, you can think about projecting x0 in this set. It is convex and closed. And then you have this orthogonal projection from x0 into this set. And then you define x1 as this projection. OK? x1 is the projection of x0 in omega. If you use the polarization identity in Hilbert spaces, if you use the polarization identity, you can derive this equality here. Observe that in the left-hand side, we have the difference between the iteration error in the point x1 and at the point x0. If you are able to prove that the right-hand side is negative, for instance, and then you obtain the monotonicity of your method. This part is already non-positive, and you need to prove that this part is non-positive. But in Hilbert space, this is actually easy, because if you look at these vectors here in red, this is more than 90 degrees. And then this inner product becomes negative, or at least non-positive. And then you obtain the monotonicity of your method. So in the iteration x1, you are closer to the solution as you are in the last iteration. This is the idea, mainly, in Hilbert spaces. And you can prove also this equivalence here. x1 is the orthogonal projection of x0 in omega if and only if x1 solves this optimization problem. We minimize this functional subject to x in omega. We find among all the vectors in omega that one that is closest to x0. Okay? And now I will present the method in Banach spaces, how we can do that. So we need to know a little about subdifferential and Bregman distance. The Bregman distance is defined, the subdifferential is defined for a convex functional. We have a function of phi from x into the extended real line, which means that phi can be infinity at some points. And then we pick a vector x0 in x, and we define the subdifferential of phi at x0 as all the elements in the dual space of x which satisfy this inequality here. This part here represents a hyperplane, and this part is phi at x. This means that the graphic of phi stays above this hyperplane here. This is the idea of the subdifferential. It's a kind of generalization of derivative. And the Bregman distance uses this idea to define this notion of distance here. If you have an element in the subdifferential of phi at x0, you define the Bregman distance in the direction of xi0 in this way here. It's actually only the difference between that part and that part. So if you have, for example, here is x, and here is r. If you have a functional like this, for example, or like this, you have a corner here. Right? This is phi. This is convex. If it is not differentiable at this point x0, but it can be subdifferentiable. If you can use here a hyperplane with equation f of x equal phi x0 minus c0 x minus x0. So saying that x0 is in the subdifferential of phi, say that c0 is in the subdifferential of phi at x0 means that this hyperplane stay below this function f. And the Bregman distance is simply this difference here. If you pick x here, then this difference here is the Bregman distance between x0 and x. It's a kind of linearization error or something similar. Well, if you have better, good functions phi, I mean very convex or very smooth, then then the properties of the subdifferential are better, and the Bregman distance becomes also better in the sense that the properties are similar, the properties we want to have. For example, if phi is Gateau differentiable at the point x0, then the subdifferential is only one point, has only one point. That is the Gateau derivative. And, okay. For example, in Hilbert spaces, if phi is this functional here, then the Bregman distance is only that. And a very, very important equation or identity we have for the Bregman distance is the so-called 3 points identity, is this one here. Observe, this is very, very similar to this equation here. We used to prove, for proving the monotonicity, it's almost the same. Look at that. Here is the iteration error. This is already non-positive. If we can prove that this duality pairing is non-positive, then we get the monotonicity of the method. So this is the idea in Banach spaces. We mimic the ideas in Hilbert spaces, almost the same thing, actually. Then the projection method in Banach spaces is that. We have x0 here, x plus here. We construct a set, omega, which is closed and convex, and separates x0 and x plus. And then we project this point here at the set, projecting this sense. We solve this optimization problem. We find among all the points in omega, we find that one which is closest to the x0 using the Bregman distance. So the situation here is something like this. You have x0 here, you have omega, and then you observe the balls generated by the Bregman distance. They could be a little different balls, but in the first, you increase the radius of these balls, and in the first point, in the moment that one of these balls does just touch the set omega, you have your projection here. So it depends on how is this ball using the Bregman distance you are using. It depends on the functional you are using. Okay, let's go back to inverse problems. Here is again the problem we are interested in. And here is very important, how we generate this set omega which separates x0 and x plus. It is defined in this way. We fix mu greater than 0, and then we define this set here. Of course, it is convex and closed because A is linear and bounded. And to have the property that omega actually separates x0 and x plus, we need to enforce these two things here. If mu is greater than delta, then the solution, all the solutions actually will belongs to omega mu, because we have a in x plus minus y delta. This is the same as y minus y delta, and this is less than or equal delta. And this is less than or equal mu. This means that x plus belongs to the set. And the second one here is obvious. If mu is less than that, then this point does not belong to the set. Okay? So we need to pick this mu between delta and the residual in the last iteration. And then we have all we need. Omega is closed, convex, and separate the points. And then we need only to solve an optimization problem in order to project this point at the set. Is this optimization problem here. This is the set omega. And here is what we want to do. We want to find the point in this set omega which is the closest to x0. And this is a very nice lemma which connects this optimization problem with Tikhonov regularization. Observe that this is the Tikhonov functional. Well, it's not exactly, because I put lambda here for it's easy for some reasons I will show later. But you can use, for example, alpha equals 1 over lambda and put alpha here. Then you have the Tikhonov functional. It's the same thing. And this lemma tells you that if mu is between delta and the residual in the last iteration, then finding a solution of this problem here is exactly the same thing as finding a lambda such that the residual, the norm of the residual evaluated at in the correspondent minimizer is equals mu. So this is maybe not so easy, because you need at the same time finding lambda, calculate the minimizer, and then evaluate the norm of the residual. And this needs to be equals mu. But observe that mu is in this interval. So you have some, it's not so difficult in practical situations. So as we need mu in this interval, we can define it as a linear, not linear, convex combination between these two parts here. And, well, this eta here, I want it to be not so close to 0 and not so close to 1, because I want stability and I want that my method is not so slow. So I need these bounds here. Well, here we have the method itself. We start with x0 in x, and we need to find a vector in the subdifferential of phi at x0. You have some ways to do that. You can solve an auxiliary problem for finding that. Now we fix eta min and eta max and tau larger than 1. We stop our method with the discrepancy principle. So we stop in the first iteration when this inequality is not observed. And what we need to do, our task is in each iteration we need to find lambda k such that the minimizer of this Tikhonov functional, the residual, the norm of the residual of the minimizer of this Tikhonov functional is in this interval here. This is maybe not so easy to do, but it's not impossible. In some situations, you can do that very fast, in a very practical way. But observe that it's not so easy too. You need to find lambda, and then minimize this functional, pick this minimizer here, evaluate the residual, and observe that if this residual is in this interval or not. Okay? And then you use that, the iteration here, for updating the vector in the subdifferential of phi. You can prove that if this vector is in the subdifferential of phi at xk minus 1, this one is in the subdifferential of phi at the point xk. You need it later for using this Bregman distance here in the next iteration. Okay? So this is the method. And now, I'd like to show you the main results we can obtain using this method. Observe that this choice of this lambda here, it's not made a priori. You find it using the information you have in this iteration xk. Okay? And using that, you are sure that your residual satisfies that. And then you have a rate for you know how fast your residual will decay. So you know a priori how much steps you need until termination, or at least a bound for it. This is here in the main results. This is the assumptions we need. X is linear. Linear is not here, but it needs to be linear and continuous. Okay, the inverse problem needs to have a solution. And phi, this is very important. It needs to be weakly lower semi-continuous and uniformly convex. And we have also some assumptions on spaces. X is reflexive and Y is uniformly smooth. This is a little stronger. We don't need so much, but okay, it's enough for what we need here. And using these hypotheses here, we can prove many things. The first one is, of course, the algorithm is well-defined and terminates. So the Tikhonov function always has a unique minimizer, and it's always possible to find a parameter, a regularization parameter, which leads to the minimizer satisfying the inequality we want. The second one is that we know a priori how many steps we need until termination, because we control the rate the residual decays. K delta is the last iteration. It's the first iteration which satisfies the discrepancy principle. So it's our last iteration in our method for the noise level delta. And this is maybe the most important inequality. We can prove using this 3 points identity I show you from Bregman distance. We can measure the distance between the consecutive error iterations here. And it is less than that, which depends on the residual at the point xk. This is a key inequality for proving convergence in the noiseless situation. Further, using this hypothesis, we can prove that among all the solutions of the inverse problem, there is one which is the closest to x0. This is called the minimum norm solution. Minimum norm in the sense of the Bregman distance is the closest to x0 using the Bregman distance. Okay? And in the noise-free case, if delta is 0, we can prove that the sequence generated by this method will converge to this x tag, this minimum norm solution, as k goes to infinity. And if you have noisy data, then you know that as delta goes to 0, then your method will return vectors which are closer and closer to the x tag. So this is the regularization property. You can prove that using the hypothesis I just showed you. Well, here are some important references. This idea of these projections, interprets this method as these projections, I saw first here in this work from Leitao and Banach Spaces. And this is a very important paper by Martin Hanke, where he uses a similar idea for nonlinear methods in Hilbert spaces. I'm not sure if he was aware on this geometric interpretation, but the method is pretty much the same. Okay, thank you for your attention.